Welcome to Under the Microscope, your go-to podcast for materials and nanoscience. I'm your host, Dr. Pranatik Sirsagar. Together on this podcast, we explore the fascinating world of nanoscience, where the smallest discoveries make the biggest impact. Hi everyone, welcome to Under the Microscope Season 7, first episode of Season 7 in 2025, and I'm very excited to introduce you to today's guest and the next QuanTour Hero. QuanTour is an official outreach project funded by the German Physics Society, and the Science Talk is the official science communication partner of the QuanTour project. Today we have with us Nika Akopian, who is a professor at the DTU, which is Technical University of Denmark, located in the greater Copenhagen region. And Nika is going to tell us everything about his research, about his career journey, about what keeps him in science, what barely keeps him in science. So with that, welcome, Nika. How are you?
Hello. It's great to be your guest and ready to answer your questions.
Could you please explain your research to us in super simple words?
One of our main goals, or the main research focus, we call it a multi-qubit project. It's an ERC granted project. And what we want to create, it's, maybe I say in general first, a multi-qubit device with photonic interface. And there is a reason for that. So it goes along with current developments of quantum technology, quantum science technology, and it goes maybe more directly towards developing a prototype or something that will work as a quantum network, maybe first as a prototype and then has a potential to scale. And what I want to explain why it's connected to quantum internet or quantum network, as some people call, and then why it's multi-qubit, where does the device comes in, and why there is a photonic interface. So again, we want to develop a multi-qubit device with a photonic interface. When I ask you or your listeners or your audience, what the first thing that comes to their mind when they hear quantum, it's probably quantum computer, right? Most of the people understand what is that, right? And quantum computers are already around the corner. Google has one, IBM has one, they're improving every year better and better, right? And then it has been promised, and we are waiting for the promise to come true, right? That's only a multi-qubit quantum computer will do things better and also differently than classical computers do, and something that classical computer cannot do, right? And so single qubit quantum computer doesn't make much sense, so will not do much, but multi-qubit with thousands will get the promise done. And the same thing goes for quantum internet, right? So if you make a single qubit quantum internet, that's not much. It probably will be only show like a proof of concept. So we want to really make a multi-qubit device, right? That's part of multi-qubit. And we also want to make it with a photonic interface because as we all know, and as many people know already, that photons are the only way to connect remote large quantum system or any system. So even internet today, how it's working, how you see me and I see you, it's via optical fibers where photons are sent around, right? And they carry information. So for quantum internet will also be photons, but it will just one photon, single photon that will carry quantum information. That's why it's very important to make this multi-qubit device with built-in photonic interface such that it can connect to one quantum computer or quantum system here and another quantum system somewhere far, one here, as I always say, as an example, one here, maybe another in the moon.
We did cover it a little bit with the previous QuanTour guests, what a qubit is, but could you just do a very brief introduction, like very simple terms, what is a qubit? Because then we can also then get into why single qubit is not good enough and we need multi-qubits.
We can try, but I believe people have heard of what qubit is many times. I just say it once again, right? If you take a bit, like normal computer works, it can take only value of 0 and 1. Qubit can take value 0 and 1 and any value in between. And that essentially is, right? That's why it's a conceptually different way to manipulate with information, because not only one, because it's also anything in between and at the same time. And there are multiple ways to realize qubit, and we have our own way.
Okay, this is good. So then you say we need multi-qubit, but we also need single photons, and with the optical fibers, the information is transmitted through multiple single photons, and with the quantum, like the multi-qubit system that you are working on, you just need one single photon to transmit the information.
Yeah, so yes or no. Indeed, information is transmitted using photons, but for quantum information to be transmitted, we need only one photon, right? So all the information will be encoded or transferred from a multi-qubit device to a one photon, or even in better scenarios, a single photon that will travel along in optical fiber or free space, to the clouds, to the moon, maybe, doesn't matter where. It can be entangled with this multi-qubit device, and it can keep the entanglement along the way. And a single photon, it's important because it comes from the very basic quantum principle, which is called the no cloning theorem. It means, in simple words, that quantum information can only exist in a single copy. Or I have it, or you have it, or someone else have it, right? It's not that me and you can have the same information in two copies. And that's why it's also impossible to make a copy, right? So that's why if I encode my quantum information in a photon, it will be just this photon. Then if I cannot have multiple photons having the same quantum information because of this no cloning theorem, because of the fact that we cannot make a copy of quantum information, right? That's why it's in a single. So there are advantages, but you can probably realize that the difficulties also come from here, because a single photon, if it loses, we have to create it again.
Yeah, definitely. Okay, so we did have a bit of the no cloning theory. Only you have the key and I have the key, and if someone tries to break in, then the photon is okay, done. No, this is not working. And also with the entanglement, I think what you mentioned, the information transfer, let's say from Germany to Copenhagen or Germany to Denmark, it is, I think we covered that with, you need amplifiers.
Yeah, no, we call it quantum repeaters, right? Yeah, that's
repeaters.
Maybe
yeah,
they're
exactly.
Quantum repeaters. Yes, so special devices that can help to transfer quantum information over long distances. Right?
Exactly, and then there is like the single photon that is going from point A to point B to point C to point D to reach the Z. So from Germany to Denmark, let's say Mannheim to Copenhagen, then there are multiple stops. And so that's also interesting. And then when you say that the information is transferred in a single photon, what does it mean in the sense that, let's say now we are recording or we are having a conversation online? Is it like one photon every second? I'm trying to understand what would that mean in real life sort of example?
That depends how it's realized, right? It can be realized in two ways. One, it's already nowadays, it's called QKD, quantum key distribution. This is send, receive information. I send you, you receive it. Send, receive, right? It's one way. So then we can generate key with single photons and then also transfer information. Another way would be through distributed entanglement. If you have a node and I have a node, we distribute entanglement between them and make sure that my node and your node are entangled. So if I manipulate something here, rotate, at the same time happens there. And that's another way. Again, I'm not going in detail, but that's not just send receive. So I entangle two systems and they behave as one system. That's also a way to manipulate information, which is, or at least two systems which are in different remote locations, right? Yeah, hopefully it gives some light also to that question.
Yeah, it does. It definitely does. So you mentioned, so you're doing the multi-qubits, you're working on the multi-qubits. So what does that mean in terms of the materials or nanoscience, or do you do the fabrication? When you go in the lab, what kind of things does your group does? Do you fabricate the material? Do you create the quantum dots? Do you grow the quantum dots, or how is that from the material science perspective?
Very good question. So we collaborate actually. So not everything we do, and it's nowadays probably it's impossible that one group does everything. Maybe it's possible, but at least it's very difficult to keep up with the best level. There are many platforms where multi-qubit devices can be realized, and the multi-qubit device with photonic interfaces can be realized, and all platforms have their advantages and challenges. Just for example, this quantum computers today are made with superconducting qubits, namely transmons. Let's not go into details, but but this may be right now is the most practical quantum computer today. But those transmons or superconducting qubits, they do not have native built-in photonic interface. So, for instance, one Google quantum computer cannot communicate natively or easily with another Google quantum computer, and definitely not with an IBM quantum computer. Right? So, we need to find some physical platform that has several advantages together. So, it has to be nanoscale, so it has to be small, scalable, so it can make many. And when it's a nanoscale, then many means it's still small. Right? It has to be with built-in photonic interface, so this device can have native interface ideal to send these photons, and those photons are entangled with the device. And when we search for such a platform, one of the promising candidates is quantum dots, because quantum dots have electron which is in the device. This quantum dots have, they already have been proven they're excellent source of single photons, excellent sources of entangled photons. Now cluster states and are demonstrated with those and whatnot, right? And so they can host an electron. They can send a photon around, which will be sent out, and they have built-in interface, and they in principle can be scalable. By the way, they also have nanoscale size, right? It's just few nanometers by few nanometers object. They in principle can be scalable. But here come the problems. Despite the 30 years of research with quantum dots, most of the groups have not gone. There are only few groups that did something with just 2 quantum dots, and definitely not 3 and not 4. Because in the way the best quantum dots are grown today, there is a fundamental reason that it's difficult to scale them. People can grow multiple quantum dots in a nanowire, for instance, but they are not able to control them such that each quantum dot is exactly the same if we want so, or different, and if different, then by our design. It has not been demonstrated. And there's a fundamental reasons with that, because it's one material can be intermixed with another material, and so on and so forth. So we came up with another idea, what we call crystal phase quantum dots. They are not made from 2 different materials. And again, the fundamental problem is if we have gallium arsenide quantum dot, it's typically surrounded by another material, let's say aluminum gallium arsenide. And even if we make interface between the 2 very sharp materials, will always intermix, and one will go here, one will go there, and the interface is smeared and not sharp. So that's a limitation explaining why we cannot make multiple quantum dots and control their size, dimension exactly as that we want. So with crystal phase, it's very different. They are not made from 2 different materials. They are made from the same material, but with different crystal structure. And when I say crystal structure, it's how atoms are assembled. They can be assembled as a cube or as a hexagonal, for instance, and different assembly of the atoms. It's a different crystallographic phase, what we call. So again, now imagine a nanowire, and here I assemble all my atoms as cubes, and here I assemble all my atoms as that's possible to do in a nanoscale object like a nanowire like this. And just to put dimensions, this can be few microns, and the diameter here, it's just few tenths of nanometers, let's say 50 nanometers diameter and few microns length. Then it's the same material but different crystal structure. And now crystal structure cannot intermix. It cannot be half cubic, half hexagonal. Or it's cubic or it's hexagonal, just because you cannot put atoms half here and half there, or here or there. That's how binaries there are assembled. Now, if we can control assembly of atoms being in a cubic phase or in hexagonal case, then we can make these crystal structures in the way we control them. And it turns out that this small section of, let's say, cubic structure surrounded by hexagonal structure acts as a semiconductor quantum dot that we know very well. If we can master this gross control, right, choosing how atoms will be formed in a crystal when we grow nanowire in cubic or in hexagonal cubic, if we can control this during the growth, then suddenly we have the accuracy of a single atomic layer, and the better you cannot even have or imagine. These quantum objects that we create, we can have, let's say, a hexagonal nanowire, and then just 2 atomic layers of cubic phase there. That will be a single quantum dot. And imagine we have a control, so we can have multiple these insertions, and we can now make all of them the same, all of them two layers here, 2 layers here, or all different, but then by our design, 2 layers here, 3 layers here, 4 layers here. That's a control we can have with such interplay with the growth technique, with the crystal structure, having built from the same material, gallium arsenide or indium phosphide, just to name a few. but with controlling the crystal structure or crystal phase. That's our way to scale, or to at least to solve this problem with or challenge with quantum dots. Is that despite 30 years of research, single quantum dot is perfect. Some groups demonstrated great example with two, but then it stopped. So we came up with the idea. We developed the concept. We conceived new type of qubit with advantages. We call it location qubit. Maybe I won't go into detail unless you ask. Then it really comes if you can master the growth, right? And there is a special machine. It's a growth machine. There are two methods of growth. With one is MBE, molecular beam epitaxy. Another is MOVP, metal oxide vapor deposition. Two methods to grow nanostructures and also quantum dots. But those machines can be combined. It's very difficult, but can be combined with in situ TM, transmission electron microscopy. So we can see layer by layer during the growth, like we really even atom by atom, how things grow in MB reactor and also in MOCVD type of growth. Again, layer by layer. And even if we made a mistake, we can edge back or control it and correct it. And again, we collaborate and with our partners, and so far the best I know, there are only two machines in the world, maybe more now, but I'm not aware. But I would have known probably, but unlikely. So one is in Paris, in France, and another in Lund, in Sweden, and we collaborate with both. So that's where our samples are grown. Of course, it probably sounds fantastic, but there are challenges there. To sum up, we are developing a method to grow multiple quantum dots with different technology to make many of those all the same, all different, because we want them different. And that will be our multi-qubit device. And because of its quantum dot, it will send a single photon out and has built-in photon interface to the quantum device, which stays in the lab or anywhere.
Okay. Many questions, because I am a material scientist by training. My PhD is in materials and nanoscience. So for me, this is super fascinating. And also, thank you for explaining the reason behind growing it like crystal, from the crystal structure perspective, controlling the growth from the crystal structure perspective instead of two elements mixing together. So I know that Armando grows relaxed quantum dots. Ronaldo does stressed quantum dots, and which in his case is like, okay, growing them and then using magnetic or electric field to align them in the right direction, in the direction that you want, so that they all function collectively together. And then Carlos does boron nitride quantum dots. Boron nitride, like with the cavities and stuff. And these are the ones that you can use because at the end of the day, the purpose of the quantum dots and also the Q source that is traveling around, which you will also be hosting, is to emit this single photon, right? It all comes down to the fact that, okay, we should be able to emit a single photon. That's why it is the single photon emitter. And then Emmanuel does site controlled. And there we spoke about like the scalability and control of the quality of the quantum dot, right? So this is what we have covered so far. So I'm trying to figure out where do your quantum dots fit in this picture. I'm trying to organize that in my brain, and probably also the listeners or watchers are also trying to align that. Where do your quantum dots fit in?
I think I said already, but maybe I say it again. So most of the group have just one quantum dot, different kinds, this kind, that kind, but and all have their own advantages, disadvantages, and there's a lot one can do with a single quantum. What we do, we want to break this and then make multiple quantum dots where we control each quantum dot, and we put them in a nanowire. So one here, second here, third here, fourth, and all can be quantum mechanically connected. So that's why it's a multi-qubit. So it's all of this everywhere. There is a quantum, and we can control each of them the way we want. Again, if I put three here, we can make three the same or three different because we design them differently. And that's huge advantage to have them. Of course, we have to demonstrate that everything works, right? So by now we can create structures like this.
You also mentioned there is like the in situ TM, which is just like, what? So you probably have a lot of pictures and lots of videos as well with the time lapse as to where
videos. So that's I have to give a lot of credit to our collaborators. So we don't do these videos, but our collaborators in Paris in the C2N laboratory, it's the University of Paris-Saclay together with the CNRS, and the other group is Lund University, it's the Department of Nanoscience. We are collaborating with them, and they have beautiful pictures of real-time growth of nanostructure. You really see atom by atom how the devices layer by layer in real time is formed, right? And that's visualization, or that's real-time view, enable us to see real-time what we grow, if it's a cubic or if it's hexagonal, and then even control or change if accidentally the growth condition were such that it's not what we want.
This is brilliant. Can you please share the links or the videos with me with of course, the source? I can then add them in the video.
The permission, but probably, yeah, that will be possible.
So let's go into your career journey so far, because I'm pretty sure a 5-year-old or a 10-year-old Nika was not saying that, oh, I'm going to be a professor and I'm going to be making these beautiful quantum dots in Copenhagen. So could you tell us a bit about your career journey? How did you get to where you are today?
Yeah. I guess I was not satisfied with answers, how things work, that I was getting when I was a kid, and so on and so forth. And then I realized that physics can answer most of the questions, right? Even to the deepest level. That's probably why I chose the path to do physics. Also, I like computers also, but at some point I had to decide and end up with doing physics. My bachelor, master, and PhD were Technion. It's Israel Institute of Technology in Haifa. And when I went to Delft, I got one of the best grants there for young scientists and stayed longer in Delft. I had a grant. It's kind of a first independent researcher grant. I know some people maybe heard of program Veni Vidi Vici. They have this, that's a Veni part, there's the first part which they give for a doc. So then I stayed longer in Netherlands, and then did some work jointly with Eindhoven University. And then time came to form my own group. So I was looking around, interviewed here and there, and decided to join DTU. And still very happy here. So that's why we develop our multi-qubit devices.
In Technion, in Haifa, you have, I think, the beautiful view of the city also, because the university or the campus is a bit on the...
Yeah, also the Bay Area.
Also the Bay Area, yeah, I remember, because I was there for recording a bunch of videos at the beginning of the Science Talks YouTube. This was in 2018, I think, or 2017, 2018. So yeah, Technion that's the MIT of Israel, right? That is the place for university. Israel has lots of great universities.
Israel has many other good universities. Weizmann University is good. Tel Aviv University is good. It's of course, I'm from Technion. I would say Technion is the best, but it would not be fair to... Israel has many good universities, actually. It's very well positioned.
Even Tel Aviv University. It's just, there are just so many great universities. And Technion is, I think, known for engineering, I think. And Weizmann, of course, for fundamental research.
Not fundamental. There is a lot of fundamental science going on, so it's. I don't think it's easy to distinguish right now. For instance, Technion doesn't have humanities and things like that, right? So maybe it's more like math, tech, biotech, chemistry, this kind of things, right? Natural sciences, but still fundamental science and connection to technology and startups is definitely there.
Yeah, absolutely. One of my very good friends actually has a civil engineering degree from Technion. And I think her opinion has also kind of created this bias, because she's like, oh my God, Technion is the best. So, okay. And then you were in Delft. So you won the Veni grant. I think it is like the starting grant equivalent of sorts in terms of the European Research Council, like if people were to draw their parallels.
So exactly. So we have ERC starting, consolidator, and advance. That's a European level, and many countries have the same thing, the same competitive grants at the national level, right? So if and then ERC starting, consolidator, advance is compared to Veni Vidi Vici in advance. Then I moved to Denmark. Yeah, and one of the reasons to move to Denmark, because I also applied for different grants around, and in Denmark there's what's called the Willem Jan Investigator. It's a private company, also one of the most prestigious grants there for young researchers. And I got that, and that was a lot of driving force towards there, because I already had my next grant in Denmark. So that's easy to accept, because some funding was already there.
Okay, so you have the ERC consolidator. You also in the past had the national equivalent from the Netherlands to the ERC grants, and you also kind of similar.
Yeah, it's also on the national level. It's maybe equivalent to the starting grants also. Yeah, very good when you have those. Yeah,
definitely. That's quite interesting. And research grants are very, very important. In all the different kinds of research projects that you were involved in, you are involved in, if you have to pick one research project that you can talk about, could you pick one and explain it to us in simple words in the section we call In Other Words?
Actually, that's my career path. When I started even my PhD in Technion, there was entangled photons, very important what I do now. Then in Delft, we discovered crystal phase quantum dot, and we came up with the idea of combining natural atoms with artificial atoms, so quantum dots with rubidium. All these are small pieces which are connecting together and making path towards what I'm doing right now, which is a multi-qubit project. So what happened in Technion, in Delft, in Eindhoven, and it's one path that brings from the beginning towards multi-qubit projects that we are doing now, understanding the challenges and trying to solve those and come up with new science and potentially and very hopefully new technology, which hopefully will be very useful.
You also mentioned artificial atoms there. Very sneakily, you just mentioned it. What is that about?
The other name of quantum dots. It's just quantum
that's
dots.
just a different name for a quantum dot.
Yeah, exactly. Because quantum dots, they behave like an atom. It's a atom where it's if take a hydrogen atom, it's a two-level system. Electron is here in the ground state. When you excite it, rotates there in a simple way. But then it can grow back and emit a photon. So it's a two-level system. And quantum is also a two-level system with a big advantage or with challenges also. You can design that the way you want. That's why it's artificial atom. Coming back to our project of multi-qubit devices, that's we use this possibility to design our artificial atoms the way we want, because we will do what we want to, not what just nature give us. If I limit myself to a platform like a single atom or trapped ions, very good platform. So I'm not going to say anything bad about it, but they still have limitations, nature given. They take atom, that's what it is. That's the wavelengths. Not much you can do. Of course, they have the advantages. But artificial atom, you can play, you can design not maybe everything, but many things, right? And it still behaves like an atom with its advantages and challenges. So that's why we call artificial atom. And now for what we do, it actually makes sense because we design multiple atoms, artificial atoms, and use this possibility to change. Again, we can make all the same or all different by our design. So it's quantum dot, but it has its meaning in the name. It's not just another name. It's with its own meaning.
Interesting. Okay, thank you for explaining that as well. That makes sense. With the multi-qubit, artificial atoms are essentially just quantum dots designed in a way that they function or behave like atoms.
Exactly.
In the sense.
Yeah. The advantages and challenges, right?
Of course.
Yeah.
Yeah, it's not a one size that fits all. There is no silver bullet like, oh yeah, this is for everything that we do and this is no, everything has advantages and disadvantages. Every system, every material has advantages, disadvantages in a particular system, in any kind of system that you use. Now that makes a lot of sense. And Nika, it's very clear to me that you love the research aspect of being a scientist, because every time you speak about the science, about the research, about the scientific concept, there is this shine in your eyes and you're so excited.
It's because many things also work. We come up with idea and it works. Not every idea, but many do. So that's
many do. Yeah, that's rewarding. Right?
Some of the many are also useful ideas. That makes even us more happy because people can use it.
Absolutely. So, other than the research aspect, what else do you like about being a scientist? Because the higher up you go in your career or the longer you stay in research or in science, you get more different kinds of responsibilities or different kinds of work, which is more than just, I'm putting just research in quotes. But what else do you like about being a scientist, about your life as a scientist?
Yeah, so my childhood question was answered. So, I want to find a way to answer the questions. Of course, I don't know all the answers, but at least I'm convinced that most of them science can answer. But what I like now, it's a freedom. I can do what I like, as long as I can get funding for this, right? But that's a big thing. I do what I like. Again, I have to be aligned with where money comes from, right? That has to be useful for this. But if what I like overlaps with what the world needs, then it's a good overlap, right? So far, I'm lucky to like what the world needs. I have freedom within this boundaries, at least, to do whatever I like, and it's also useful. It makes impact not only for me, but for others, for people, and and for technology, and likely in far future, but hopefully in near future also.
In near future, yeah, definitely. So the freedom to choose which scientific question you're going to go after next.
Yeah, and also freedom to create. We are not only looking for questions and answering those, but we're also creating things. Not all the time, but this freedom to create, it's or to do more general. It's very important.
Yeah, definitely one of the most important things. You're absolutely right. So from what keeps you in science and the research to what barely keeps you in research. So if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
Things change over the year. It's very difficult to wish something general, but right now it would be better to have more funding. And another thing, it's bureaucracy. So we do all kind of things which are not science related, but we have to do. Filling forms, doing reports. Sometimes it's difficult to find the thanks in what you do. Of course, you know it's needed to keep the big machine rolling and going. I mean, I understand that, but maybe it's not most efficient. Also, I can't come up with a better idea, but just I wish there would be less bureaucracy and we could be more focused what we do the best.
More funding, less bureaucracy, and third wish?
I don't have a third wish.
You don't have a third wish? Everything is good?
I think, yeah.
No fancy equipment or anything?
Yeah, but that comes with funding, right? So, then the wish that what we do that will be successful and will eventually end up the way we want or even better. I think then
success of the projects.
Yeah, success of the project, right? Because we put with the importance of it, and there are challenges, and I wish we will overcome these challenges and find solutions fast.
Yeah, absolutely. Yeah, that makes complete sense. I completely understand. Less bureaucracy, more funding, and high, let's say, project success rate or experiment success rate. Let's just go with that.
Yeah,
100% success rate.
I will separate this bureaucracy. Maybe bureaucracy is the most important because funding is there, right? It's just better to have more or easy access. Write less applications, but things like that. But it's hard to complain that there is no funding at all. So there is funding, but
more funding in the future, like more sustainable, sort of like longer term funding, maybe. Or regular funding. You don't have to be realistic, Nika. This is where you go crazy. You can also ask for unlimited funding. You know what is stopping you from asking for unlimited funding, right? You don't have to be realistic
I'm
here.
not sure unlimited funding is good, so I have to be connected to reality also.
I'm trying to give you as much freedom to ask for anything you want. You can ask for a better coffee machine for your group. You can ask for anything. Are you being too realistic? But no, that's okay.
I'm very happy with what I have. It's just I wish the number one thing to less bureaucracy, and only then comes funding, and I still have to be able to find a good balance. But if it would be less,
you won't complain if it is less.
No, I will be happy actually, a bit more happier than definitely not complaining. Yeah, just resources and no bureaucracy. And resources is not only money; it's people around. It's time and in a general understanding what resource means.
Continued resources and less bureaucracy. Let's just go with that. Yeah, something like that. Yeah. Okay. Perfect. So then, before I let you go, Nika, I have one last question for you, and that is about your time on our BlueSky account of Under the Microscope. So for anyone who is unfamiliar with the concept, our account on BlueSky is called Under the Microscope, and this is a rotation curation account. This means that on a regular basis, there is a new scientist who is posting from this account for one entire week, starting from Monday till Sunday. So, Nika, what can the followers expect when you will be posting from the BlueSky account of Under the Microscope?
I think I will make it easy. I'll just show what we do in the lab. Hopefully people will like it. Explain here and there, day by day, challenge by challenge. Maybe it's nice to see daily challenges. Maybe we'll have
It will be.
Okay. But
it will be great to see. Also the videos, the in situ videos.
Yeah. I guess the best when we just show real life things, and every group is different, and maybe we can learn from each other here. I will like to explain what do we do in an easy way, hopefully.
Absolutely. Perfect. Then thank you very much, Nika. This was great. Thank you very much for taking the time and looking forward to now your posts on BlueSky. Thank you for taking the time. It was lovely speaking with you.
Thank you very much too. Yeah, it was Great pleasure, and I hope it'll be something useful out of the time we spend, and will help some people that listen and watch.
Definitely. Yeah. Definitely it will. I hope you enjoyed this episode, and if you are not following the podcast Under the Microscope already, please do wherever you're listening right now. If you're watching on YouTube, please go ahead and subscribe to it. If you're listening to Under the Microscope on Apple Podcasts, feel free to leave a review. That would be wonderful. If you're listening on Spotify, do share in the comments. How did you like this episode? What were your key takeaways? And please do follow Under the Microscope everywhere. This is absolutely for free for you, and it means the world to me, and it enables me in bringing more and more amazing guests to you. We have big plans for season 7. Thank you, and see you in the next one.